Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you out with numbers 24 and 25 in your homework over Gauss's law. So, all right, starting with number 24. Total charge Q distributed uniformly along length L, consider the Gaussian surface shown. So, I guess I would start with this. Calculate the appropriate charge density, right? And because this is a linear type of problem, right? The linear charge density you get by taking the total charge divided by total length. Again, there's three types of charge density. This is the one we use for charge over length. This is the one we use for charge over area. This is the symbol we use for charge over volume. So the ratio of these two is the charge per unit length. Now, the Gaussian surface is drawn. That's what this is supposed to be done for you. This has three surfaces to it. It's got this side surface. Draw a normal on that side surface, keeping in mind that outward positive. Then you've got this, I like to call it the beer can surface, this outer surface. Draw a normal or two on that surface. Again, outward positive, right? Then you've got a surface over on the right somewhere here. Again, draw a normal. So there's three different normals. Now, Gauss's law, I will write it out for you, says the total electric flux, which is the sum of all the EA cosine thetas over a closed surface, is equal to 4 pi k times the charge inside the surface. So let's see, what is the electric flux through the face shown? Basically, that's this, right? That's the total flux through that closed surface. And as we kind of look at this, the entire thing here, these two things, this is probably a good place to answer that, because the charge inside the surface is this stuff right here. And the Gaussian surface has a radius r and a length L. And you should be able to pretty easily, using your charge density and the geometry of the surface, come up with an expression for this stuff inside of it. I made a big deal about all the normals. Those will show up here a little later. Let's see, what is the charge density and how much charge is inside the Gaussian surface? Actually, I guess we're doing this first, okay? That's what I just talked about. As far as getting the charge inside it. Then the total flux is 4 pi k times this. I think maybe in the future I'll rearrange those two questions, but basically you're going to be getting the charge inside with how I talked about the charge density times one of the geometries here, then go up and do this part. Find an expression for E as a function of R. So here's where, again, you write out Gauss's law. That's this stuff. The right-hand side should be known. The sum is over three sides. Now, one thing you have to realize is the electric field directions. I'm going to talk about that a little bit more. If I pick a spot, I'm just going to pick a spot like right here, close to the surface. Remember that the electric field due to a point charge is kq over r squared. Now, this line of charge is not a point charge, but you could think of it like the sum of a bunch of little point charges. The net electric field is the sum of a bunch of small things. The electric field at this point is very sensitive to distance. See how it's r squared in the bottom? That means the electric field here is due mainly to this stuff. And as far as that stuff is concerned, it is a symmetrical problem. So the electric field is basically this way, at least approximately. That should tell you something about the flux through this surface and the side surface. And then ask yourself for the electric field, the angle between the electric field and the normal. Draw a normal right here and draw an electric field vector at that same spot and ask yourself for the electric field, ask yourself about the angle between them. And that should tell you something about the cosine theta on that third spot. So hopefully that gets you through that problem. You should end up algebraically finding E as a function of R after putting all that together. And I'm sure I've got more video examples on how that's done. I'm going to move into the next one here. All right, number 25. Let's see, find the flux through each surface. So here's a picture. We've got this half circle here with this charge. Now the charge is technically outside of it, but a very small distance here, a distance delta, which is said to be small. So find the flux through each surface. It's referring to the two surfaces at the bottom, like this stuff and this stuff. Now the way you do that, or at least one way, is draw a Gaussian surface. That looks like, oops, I'd like to do this in green. That looks like this. The entire sphere. And this charge is approximately at the center, and it's definitely inside of that Gaussian surface. Now, it's not inside the gray one, but it is inside of our green one. So Gauss's law should give you an expression for the total flux through the Gaussian surface, 4 pi k times the charge inside the surface. Okay. Then recognize this. In our Gaussian surface, what fraction of that is here, basically. And that should tell you the flux through that top surface, right? So when it says each surface, there's one of them. Then decide whether or not that flux is positive or negative. Remember, outward normals are considered positive. Once you do that, now consider this thing, the original picture here, as a Gaussian surface. Let me draw that in red. Keeping in mind the flux through the outer part would be known. And keep in mind, this is not inside of that surface. So that should tell you something about the net flux through that surface. And that should be enough to get to get it figured out, the flux through each surface. So hopefully that this helps. Have a great day.